This is not live. We are going, for those of you watching this not live, I'm going to take a couple minutes for people to join in because they can't join the call until I start it. So you may want to fast forward to where I write some more stuff down. I just sent the reminder out. It is showtime now. I'll wait to see if anybody joins us or if I just talk to myself today. So, oh, there's one viewer now. That is good. 2. Ooh, exponential growth. Now, I have been told that there is a way to ask a question on this. I, of course, have never tried it because why would I ask questions of myself? So if you are on the cast and you can type a question, feel free, and as soon as I see it, I will let you know. Otherwise, you can ask a question by texting to the remind. The remind will give you a, it sends me an alert on my cell phone that lets me see what you're talking about. We are up to 4 viewers, so we are continuing the exponential growth. Just need 4 more of you, and then we will be good to go. If you have asked a question, I have yet to see it. But again, I'll wait for a minute or 2 while we wait for people to join the call. Hopefully you are enjoying the snow day today and the possibility of a snow day tomorrow with a late start on Wednesday. It is a beautiful day up here. Sadly, though, my kids' daycare closed early today, which foiled my plan of giving you this podcast before Mike had to pick up my children. So they may sporadically come in or out of the podcast as we look at it today. Hopefully you also got the message to download these notes. Nancy Stephenson from Clements High School. She is a national big guru. I got these notes at a conference earlier this year. They are good to follow along with. And just FYI, they would be good. We are up to 8 viewers now, so we have experienced exponential growth, and we just lost one down to 7. Very sad. Apparently, I bored somebody already. So I will wait about 10 more seconds, and then we will get started. Good news, no Breebach today, so we don't have to deal with that distraction. If there's any problems with the cast, again, just reply to the remind if the questions are not working on the Google Doc. As you will see, we will begin. Today, we are talking about 6.1, which is the beginning of the second part of the calculus that we're talking about this semester. We have talked about limits, we have talked about derivatives, we have talked about integrals. We are now heading into the harder parts of integrals, of the applications. The good news for you guys as students is that the chapters are much shorter. Chapter 5 is very long. There's lots of topics in chapter 5. And the good news now is these chapters are shorter. We don't need to do all of the sections for the AP test. And just to make sure we finish this year, we will just do the ones we need to do for that. Continuing on with that, though, if there is a snow day tomorrow, I will put another one of these podcasts up just so you guys aren't tempted to be so bored as to not learn anything during the day. So where are we at? We are just about at the end of integrals, and then we'll start the 4th part of Calculus BC, which is series and sequences. Good news is series and sequences, the chapters are short. The bad news is that's because they're some of the harder ones. So today we begin 6.1. What are my goals for this lesson here today? You will be given slope fields and an intro to differential equations. You'll be reminded, and I'll write it down here in a second, that a differential equation is an equation that relates x and y to their derivatives, either x prime, y prime, dy, dx. With later calculus classes, you may talk about dx, dy. But to relate equations to their derivatives or functions to their derivatives. So what do you want to learn today? Given a differential equation, you got to be able to sketch its slope field. That is tedious, but the AP test loves that and loves to make you do that. So we will talk about those. In fact, if you look through the notes packet, there are several examples, especially in AB. AB, it's almost guaranteed that they will have you do a slope field question. Then to match the slope field to its differential equation. To verify an equation is a solution to a differential equation, and then to find a solution to a slope field. So since I have a captive audience today, and apparently you guys can't ask questions, we will begin by talking about some general applications of algebra and then remind you of how we apply those to what we are talking about here today. So, Let me take a look at my notes. So first thing, we have got to go back to the fun of Algebra 1. Yes, all of you, even those of you that feel like you're too good to do Algebra 1 right now, let us look at example 1 for today, and let us look at 2 points. Let's say 3, 7, and let's make it not too difficult. Let's go for 5, and we will go for 1. Here's what I'd like you to do. A, I'd like you to find the equation parallel to the one going through these points. We have a question. You have to have a Gmail account other than the schools to ask questions. Batman asked that one. Maybe somebody off the internet, I don't know. Good news or bad news, it is free to get a Gmail account. It is advisable to get a Gmail account. And yes, the school probably blocked that because it would be useful. So an equation parallel to the one going through these points. All right, I will give you a minute to try it out on your own, reminding yourselves of the glory days of Algebra 1. Ready, set, math. It says chat is disabled for the live stream. Well, that's too bad. Let me see if I can figure out how to enable chat here while you're working on that. Batman says it's Brandon. Well, I'm sure Brandon wishes he was Batman. So chat, let me see if I can enable it here. Okay, let's see, test. See if that will work. Test, chat, and test. We'll see if you all can see that. And I'm not using my school email for this. I'm using backmymath@gmail.com because the school one was too restrictive. So. All right, reminder, find the equation parallel to this one going through those points. So you remind yourself that, oh, the first thing I need to do is I need to find the slope. So the slope is equal to y2 minus y1 over x2 minus x1. All right, then you're very smart. You remind yourself 1 minus 7 is -6. 5 minus 3 is 2. So -6 divided by 2 is -3. So if it's going to be an equation parallel to this one, the slope between those two lines is -3. Parallel, don't forget, it means they have to have the same slope. So now we could write what is called a generalized solution to this. We could write y minus y1 is equal to our slope times x minus x1. Now, if you could imagine, there are a whole bunch of equations who have a slope of -3. And if you remember, this is a slope of -1. In fact, this would be the equation y equals -x. You know, if it went down even further to a rate of over 1 down 3, that would be y equals -3x. Now, there are a ton of lines that have that slope, an infinite many above and infinite many below. This would be called a general solution. In other words, it doesn't give us the specific one, but it gives us the criteria that that one has to have. Or if you want to go back really to Algebra 1, y equals mx plus b, our generalized solution would be y equals -3x plus b, where then we could find what that b value is. However, to be able to solve the equation, to get the exact solution, to get the particular solution that would go through one point, we'd have to be given something called an initial condition. What's an initial condition? Well, it tells us one point that goes through. And just like we did in Algebra 1, we're going to do that today with differential equations. So if I told you that, I don't know, let's say that it has to go through, well, let's make it easy, 1, 7. Now, instead of having an infinite number of solutions that would satisfy a general criteria, we could now find a particular solution that goes through that exact one point. So if somebody has seen the chat, please let me know too, or reply back to it. Otherwise, I am chatting to myself. So to find that, we plug it in, because remember, we kissed this goodbye in Algebra 1. We went to point slope. So y minus y1 is equal to our slope, x minus x1. This is a particular solution that goes through that point. That will look very similar to what we do today with these differential equations. What we will do is we will be given a differential equation. We will ask if it solves a particular one, and then we will be asked to find the particular solution that would solve their equation. Any questions before we go on? You can just send it to the remind too. I'm getting those messages on the cell phone. And if I've disabled chat somehow, I am very sorry, but you can just ask questions that way. All right. Hearing none, we shall go on. So let us reminder of a solution. Let's go back to the very beginning, our Algebra 1 definitions again, and then we'll apply them today. A solution to an equation was any value that, when substituted for the variables, rendered both sides equals. In other words, it solved it because it made it both sides equal. Let us also go back, because I think a rigorous definition makes the whole lesson go easier. Let's look at a differential equation. Oh, we have, I think there is a thing with comments on the video. I think it's like the comment for Google Plus when we were commenting, but I don't think you see it. No, I don't see it. I'm sorry. I don't know what's wrong with it. We could fix that someday in class. If we have snow day again tomorrow, I can see if I can work on something for that. What is a differential equation? A differential equation is an equation that relates x, y to its derivatives. Relates x, y, and its derivative. Let's just give you one so you can see what it looks like. Like, let's say y double prime minus y is equal to 0. Now, again, differential equations is a chapter in your book, but it can be an entire class in college. Just like calculus is a very big jump in your mathematical maturity, differential equations is also a very big jump in your mathematical maturity, just because the number of real phenomena or the real things that are happening that you can solve once you have that knowledge. Now, we could imagine that the solution was any value that we plugged in. So we plugged in like a 4, it made both sides equal. We were really happy with that. A differential equation, obviously, if we plug in a 4, this won't work because we plug in 4 for y. The derivative of 4 is 0. The derivative of 0 is 0, so we'd have 0 minus 4. This wouldn't be equal. The thing that we'll have in here is y will be a function of x. Now, it just happens that a lot of differential equations have a solution that has something to do with e. You could imagine that it's very nice with e because you have the function and its derivatives. You know, e just kicks back more e's minus whatever the chain rule has inside of it. So e happens to come up a lot with differential equations. Now, this has the feel of a lot of what we did it implicit, and now we're seeing it in the reverse in differential equations. So let us remind ourselves of fun derivatives, though, and then I can go check to make sure my kids are still alive. So let's have you do an example 2 here to remind you of the fun of implicit differentiation. And of course, that's always good this time of year to get more and more review of the things we haven't done for a while. Implicit differentiation, let us look at, we have the equation x times y is equal to, oh, I had a fun one, sine y plus 4. For those of you that need additional challenge, you can put an x right there too and then really have some fun with this. It can probably take up the rest of your snow day. But for those of you that don't, here's what you got to have. You need to find dy dx. And just like Reebok checks on me, I will go check on my children. Ready, set, you try it on your own. Math. Okay, so let us take a look at that. We have to find dy dx. We remember the fun. We ask ourselves first off, this first one, it is going to be what? And that's going to be a product rule. It's going to have a chain mixed into it. So finding dy dx, derivative of the first times the second, that just gives us a y. Plus the first times the derivative of the second, x, and then we take the derivative of y, that is dy dx. And then we have sine of y, which the derivative of that would be cosine y times dy dx plus 4. And Kerrigan said, find the notes of the solution. Any value substituted for. We'll go back up real quick. Any value substituted for the variables that rendered both sides equal. Probably should be renders. I'm an English teacher. Both sides equal. Okay, so let us go back down to our fun differential equation here. Now, the question is, are we done? No, we're not, because what do we have to find dy dx? What do we have? Some dy dx, some things that have nothing to do with dy dx. So now we have to get everything with dy dx on one side, everything else on the other. In this one, it's kind of an arbitrary choice. Well, that's a 0. Thank you, Storch. That's most certainly a 0. That's going to make it easier, too. So now we have to say to ourselves, what do we do to make to get dy dx on one side? Well, we have to decide. We're going to move it to the left, move to the right. Same numeric answer. If you move it to both sides, or numerically analyzed answer. So I'm choosing to move it to the right. You could equally get an acceptable solution if you move to the left. So we have a cosine y dy dx minus an x dy dx. Look at that. They both have a dy dx in them, so we take it out. So y is equal to dy dx times a cosine y minus an x. And you'll notice we would have a differential equation because it relates to x and y and its derivative. We divide both sides by the cosine y minus x, cosine y minus x, rendering us the exact solution, once we get some more paper here, of y over cosine y minus x is equal to dy dx. Yay. Now, is this a differential equation? Yes, it is nicely solved for dy dx. Are they always going to be? Probably not. Not always. We talked about implicit. We talked about parallel. Let us review real quick where we are again so I can get it down in some writing. And I asked you at the start of the year, I told you some primitive stuff about the AP test. Now, as we get closer to it, let's add some more in. I told you at the start of the year that there's 2 questions. There's questions you have to use your calculator and questions you can't use your calculator on. Then we started talking about some of the trap questions that they seem really easy, but they're not very easy at all. Now we start to think when we get a question, we're going to say which one of the 4 branches of AP Calc does it belong in. So the 4 branches So in other words, we're now going to start to think, okay, what type of question is it? And there's really 4 things we talked about. We've talked about 3 of them. We're finishing the 3rd. The first one is the limit. We spend expensive amount of time talking about what the limit does. What does it do to a function? What happens when it goes to infinity? What happens when it goes close to a point? What does it make a vertical asymptote? What does it do to find the derivative? That's the second branch. Those instantaneous rates of change, those rules that we learn, finding the volume problems, how does one variable affect another as it goes through. The third one we're really just finishing off, which is the integral. And then the 4th one is series and sequences, as we talk about what a series does, what a sequence does, et cetera, et cetera. When you see a multiple choice question now, we should be asking ourselves which one of the 4 branches is it in? And that's when we start to remember our rules and things like our rules that should be able to jog our memory of the things that we have to remember. So now, not only are multiple choice questions, can we use our calculator or not, but also now which branch of Calc BC is it belong in? Okay, So now let us take a look at some more definitions. We defined differential equation earlier. We will use the abbreviation DE for a differential equation just because we get tired of writing the whole thing. If you continue in math far enough, there's ordinary differential equations, partial differential equations that I can remember off the top of my head that we would have to be able to find properties that we have. So there's more than just differentials. There's types as we go into it. Let's go into verifying the solution of a differential equation. So the one in the book, I mentioned probably our most primitive one. We have y double prime minus y is equal to 0. And we are going to see which of the following is a solution to this differential equation. And as always, if you have questions now, you can just text equation. We could also stop for just a second and see if anybody has any questions. And let's take a look at the following. A, we will have y is equal to, let's go cosine of x. B, we'll have, let's go for y is equal to c times e to the x. And we'll go for c, which is y is equal to 5e to the 2x. So which one of them is a solution? Now remember back from algebra 1, a solution was a number we plugged in and made both sides equal. On this one, it is a function that we can plug in that will make both sides equal. It is a differential equation because it involves the derivative and the function, the x, the y, and the derivative, or the second derivative or third derivative of that function. Give you a second to copy. Okay. So for each one of these, what as I was looking through my calc notes back in the 90s when I took this class, I'm going to just write its function is there. I have to have its second derivative, so I'm just going to take the derivative of it beneath it, take the second derivative of it beneath it, and then see if the second derivative minus the derivative would be exactly 0. Now, cosine feels promising because you say, oh, you take the derivative of cosine, you get something to do with sine. You take the derivative of sine, you get something to do with cosine. That could work itself out. Let's see. So we take the derivative, dy dx. The derivative of cosine is negative sine of x. All right. So then we take the second derivative. Could you have also written y prime? Yes, you could have. And could you have written y double prime? Yes, you could have. The derivative of sine is cosine. It does not kick back a negative, so we just have negative cosine of x. So then we ask ourselves, would dy dx, or the second derivative minus the original function equal 0? Well, this minus that would give us 2 of negative cosine, so it'd be negative 2 cosine of x. So no, that is not a solution to that differential equation. Now, just for fun, let us continue to expand on this, because you'll notice this one has a c, a constant. It probably means c could be any number that is a constant. If this was a solution, this would be a particular solution because it would be the exact thing. It'd be like y equals 3x plus 4. This one would be like y equals 3x plus b, where b could be any value. If this one works out, this will be called a general solution. Or in other words, it is a solution that has many types to it, but is not a particular solution just going through one point, like we had with the parallel lines example. So let us go through. And y prime, the derivative of e to the x, is e to the x. The constant will just carry through. This is looking good. The second derivative, e to the x, kicks us back in e to the x. So again, we have c e to the x. So if we took the second derivative minus the original function, yes, this would be a general solution. General solution to that differential equation. Now, you may say to yourself, Self, this doesn't look that bad. I know all these derivative rules. Here's the bad news of what's coming. It's very nice when they give us the function, we just have to verify it. where we will go. And what we can't do with the problems that are in that packet today is we can't look and see, like, we don't know how to find the solution. How did we generate this one? How do we find this one? That will come through a fun process that we will separate variables out and be able to find a general solution and a particular solution to that. Let's also verify this for fun. So y prime, we have an e to the 2x. The derivative of that is e to the 2x times 2. So that would give us 10 e to the 2x. Our second derivative, again, e to the 2x's derivative is 2e to the x. So that would be 20 e to the 2x. This minus that doesn't equal 0. So again, no, this is not a solution. So you can imagine, just like we had a y equals like 3x plus b, where b could have been any number, where we had that infinite number of solutions that were both moving up and down the axis, we could also have, let me see if I can do this real quick and just change it to me for a second. Now, if this does the whole thing, I'm in trouble. So you could imagine if we had our axes on there, that we could have a ton of solutions with that same slope, but that would not be the particular solution going through one point. What we will have with the particular solution is an initial condition, like a point that it has to go through. Because just like y equals 3x plus b has a bunch of solutions, we could also have a ton of those curves. You could imagine just multiplying e to the x by a constant that is just a vertical shrink or stretch to those solutions. So there would be a whole bunch of e to the x curves that we could have as a solution. If they told us the point it needed to go through, then we could find the exact solution just based off that information, then using some algebra to solve it. Let us stop, though. This is a good time. I'll give you a minute for questions. Let us stop and check up. Are there questions you have on this? And it is an awkward silence, but I'll give you a minute before we go on, because today it is crucial. In fact, as I'm giving you a minute to ask questions, when I was looking through what you covered last year, I noticed that this, well, actually, I'll be honest with you, it was Emma Burlesleiper that came up to me and was asking questions on 6.3, and I was reminding her of all the properties of slope fields that she learned in 6.1, and then she told me you guys skipped 6.1, which was unfathomable to me, because this is really the fundamental of what this does, and it's a ton. They love themselves some slope field questions on the AP exam, so it's just simply something that cannot justifiably be skipped in any rational expectation of passing an AP test. So if nothing else, can you hear me? Yes, no, just text it to there. I am getting a significant number of texts. Can we invite Breebach to the Hangout? That was the first question. Really? Seriously? Negative. I assume he is shoveling snow or whatever. If you'd like to invite him to watch, I guess, if you're at his house. Kerrigan says yes. Good, thank you. And here's the odd part. They're popping up on my screen. So Batman again says yes. Lonahan says yes. And P.S., I'm very proud of you guys. I have like more than half the class watching this. So maybe we should just do this all day Saturday and Sunday too. Just every Saturday we have a lesson, and every Sunday we have a lesson too. Nobody replied to that one though. Oh, yes, yes, yes. Oh, that's 4 yeses so far. And yes, Thomas Mitchell, I'm getting this. Yes, Brandon Storch, I'm getting this. Yes, Sam, I'm getting this. Yes, Tara, I'm getting this. Kerrigan said no, thank you. I don't know what you're referring to. Possibly the Sunday courses. Okay, so let us go through. And Tara says, Ellie says yes and no. Maybe yes to Saturday, no to Sunday. Okay, well, I guess we could take Sunday off. But it would be nice to finish like by spring break, the whole class. That would be nice. So let us, again, to get a particular solution, to a differential equation, we need an initial condition. What is, again, an initial condition? Just like it was for linear equations, it's going to be a point the solution goes through. right, just one point that it goes through. Okay, so we are going to, this one we are going to mooch. This one I'm not going to lie to you, I'm mooching straight from the book. Let's go, we have x, y prime, minus 3y is exactly equal to 0. And we are given that y equals cx cubed is a solution to the differential equation. And we are asked to find the particular solution going through, let us go 3, y equals 3, x equals -1. Not that it matters right now, but it will later on. Notice that c is outside the x cubed, isn't a part of the x cubed. Okay, first we have to, we were given it's a solution, we have to find the particular solution. So first, let's just go through and verify it is a solution. So y is equal to c times x cubed. We are going to need its derivative, so let's just take that right now. That's going to be c times 3x squared, which we will rewrite to be 3cx squared. So then let's go ahead and let's plug all this in. So we have x that just stays there. We have y prime, which is 3 times c times x squared minus 3 times y. Y, don't forget again, is c x cubed. Has to exactly equal 0, and let's hope for the best here. So we have x times x squared, that gives us x cubed. So we have 3cx cubed minus 3cx cubed is exactly equal to 0. So yes, this is a general solution to this differential equation. Then we got to figure out or get rid of c. So to find the particular, and let's even write that just so we got that in our brain, this is a general solution. Don't know who this is. Yes, that is multiplication there. And yes, that's multiplication there. Okay, so to find the particular solution, this part I didn't mooch off the book. This is different than the book, but so now I know that this is my. I want to find the one that goes through 3, -1. So I'm going to plug in 3 for y, -1 for x. Okay, so then I know -1 cubed is -1. Okay, how do I solve that for c? Divide both sides by -1, and you know that just switches the sign. So -3 is equal to c. So that's the c value that gives me the curve, because you could again imagine a whole bunch of x cubes. Which one or which vertical stretch do we need c to be to go through that point? Well, we needed to go through -1, 3. So c has to be equal to -3. So my particular solution would be y is equal to -3x to the third. That is the equation that satisfies our differential equation and goes through the point -1, 3. Again, I'll stop and check out for just a second. Questions on that? When you're asked to verify tonight, that's what you'll be asked to do. Plug in that x, plug in that y, solve for the c. And away we go. Now, bad news later on in the chapter, what we end up having to do is we have to figure out that particular solution. Yeah, we'll initially start by separating the variables. Hopefully you remember that from last year. That is a little bit tricky because then all of our derivative rules come into play, and we tend to run into a lot of e to the power of something function or e to the power of a function before we go on. Stop and check up the questions. And we're about a half an hour in, so any questions on that? Yes. Will they, Tara Storch asked, will they always give you a given to be able to find a particular solution, they have to. Just like to be able to find the exact solution to those parallel line equations, they have to tell you which point it has to go through. Yes, to be able to go through from a general solution to a particular solution, they have to give you one point it goes through or some sort of information on how to do that. As you'll see on the AP questions that we have in that packet of notes I asked you to download, they almost always give you a point. This is good. Any other questions? Saturday, this is lots of promise. If I could just get my kids to watch the iPad for an hour every time I need to teach you guys another lesson, away we could go. Imagine finishing the class by the end of March. What we do with ourselves in April? Oh, we take 28 review quizzes. I have another question. So we get a solution, a differential equation and a point. Yes, for now, for today, yes. You get a differential equation, you get a point. Later on in the book, later on in this differential equations unit, we'll just be given something like this, and then we will have to be able to find that. In fact, can I just give you a preview of what's coming since we're on that topic? Let's look at that exact one. xy prime minus 3y is equal to 0. So this is just a preview of what's coming. Don't feel like it's on your homework tonight because it's not. But hopefully you remember this from last year because I do remember helping specifically Emma with this last year. So let us think to ourselves, self, for just a second. Wait a minute. dy dx, or y prime. How else could I write that? Darn it, you said the answer, not the question. I could write that as dy dx. And if Dr. Greist or anybody from the academy is watching, they'll know this one doesn't work out on this. But what I'm going to end up doing is I'm going to want everything including dx on one side, everything including y on the other side. Because remember, this, even though we don't think of it that way, this is a fraction. This is a fraction, and we could multiply both sides by dx. In fact, let's look at that. Let's add 3y to both sides. Again, just to preview what's coming. Multiply both sides by dx. Ooh, would have been really nice if that would have been the y and that would have been the x. We actually could have solved it. Multiply both sides by dx. See, x dy is equal to 3y dx. And then we can simply take the integral of both sides. Like I said, let's just fit, since we're just previewing anyways, let's say we could just do that. Well, then then we take the integral of both sides. Well, what's the integral of y dy? Well, that's going to be y squared over 2 plus c. What's the integral of that? That's going to be 3x squared over 2. Then again, if they gave us an initial condition, we could figure out what c is and actually solve the differential equation. But again, that's coming up later, so that's what we'll do later on. Usually what you get, I say this with all love, but usually what you get is you get a 1 over y dy is equal to, like, I don't know, let's make it nasty, cosine x dx. And then, of course, you know when you take the integral, you get the natural log of the absolute value of y is equal to, what's that going to be, sine x plus c. That's why you end up getting all those e to the power of, because then how do you get y by itself? Well, you take e to both sides, and wham, wham, bam, math gets an e in there. Good question, though. So even with that, they'd have to give you like an x and a y, and you could solve that for c again. They'd have to give you a point it goes through. Any other questions? But again, that's just a preview of what's coming. In fact, that's called the technique called separation of variables. Okay, seeing none, slope fields. We talked earlier this year. Imagine yourself in and let's switch it back again. switch it to on me. There we go. There we go. Yes, save. So imagine, again, you had a two-dimensional plane. This isn't going to work in 3 dimensions right now because we only have 2 that we know the calculus of. 3 dimensionals, that'll be Calc 3 and differential equations. But imagine you had a wind going, you were just considering a 2-dimensional plane, and you saw all the areas that wind's traveling through. Imagine there were like trees and other stuff too, or there's like a fan right here and like a tree right there. And so the wind might be doing something like that to go through. We could be able to see wham, bam, math. Thank you, Starch. We could be able to see where the area would flow through, or the wind would flow through. There'd be directions in there. Slope fields are also called direction fields. That's actually what they were called when I took this way back when. But that gives us a visualization of what's happening to them as it goes through. One of the things you need to consider is when we find the exact solution to it, you want it parallel to the lines around it. Parallel to the lines around it. That's going to become important as we talk through this. But let's take out those notes that I had you print off, and let's look at those. So let's take a look. We have to draw slope fields for each differential equation. The tick marker each 1 unit. So in other words, we're 1, 2, 3, 1, 2, negative 1, negative 2, 1, 2, negative 1, negative 2, negative 3. Again, I was praying and hoping that you guys remember this from last year, but I like to make a table for these and then take a look. There are a couple things to remember. Remember, this is a slope of 0, this is a slope of positive 1, and this is a slope of negative 1. If it's more than negative 1, it's going to be even further down. If it's less than negative 1, but not quite to 0 yet, remember, it's getting flatter. Again, 1 the same way. If it's greater than 1, it's going even steeper. If it's less than 1, but not quite 0, remember, it's a little bit flatter. I like to make a table with these. So I'm going to look at the first one. Oh, there's the answer. So let's take a look at this first one. We have dy dx is equal to x plus 1. Real quick, talk to yourself. The derivative in this particular example is only dependent on what? The derivative in this particular example is only dependent on what? You can even text remind if you want to really look smart on the internet here. Maybe these 9 viewers aren't all from our class, but if the derivative on this is only dependent on what? Now, this does involve a little bit of matching because you do have to match up that you have to go from -3 to 2 from x and from -2 to 2 on y. So I'm going to start from left to right and I'm going to move down through our graph. So imagine I'm having to find what dy dx is for each one of these little tick marks. As I mentioned at the start, it is tedious, but again, on the grand scale of how hard is this, these are some pretty easy points on the AP test. So this isn't necessarily our hardest solution that we have to go through, the hardest computation we have to go through, but it definitely is tedious. So I'm going to start up here and then just go. If somebody has a more efficient way, I'm up for it. But again, on this one, I'm not seeing another way to make it more efficient. So let's start in the upper left-hand corner. So x is going to be -3, y is going to be 2. So we plug it in. Notice it's only dependent on x. That was that question I was asking you. The derivative is only dependent on x in this one. So as we come into like dealing with implicit, this one, it could be a lot worse. -3 plus 1 is -2. So our derivative is -2. Then I'm just going to move down. I move to -3, 1. Again, I just have to plug in -3, so that's also going to be -2. -3, 0. -3 plus 1 again is -2. -3, 1, -1. -3, -2. -3 again, plug it in, I get -2. -3, plug it in again, I get -2. Okay, so just normally I would not do this. I'd fill in the entire chart, but I just want to give us a picture of what's going on this. So we've done all the values of -3. If I drew a little line just like that, and these are just little lines because they are approximations of the motion that's going on in there, or the rate of change that's going on in there. If I wrote that, it would be -1. If I wrote that, it would be 0. If I wrote that, it would be +1. It's -2, so it's got to be even a little bit steeper than that. So I'm just going to draw a little line that goes like that. Again, that would be -1, so I'm going to go a little bit steeper than that. These should, in fact, be parallel. Again, that would be -1. I need to go a little bit steeper than that, so -2 goes there. Again, this is a simplified version because it's only dependent on x. It is not dependent on y, so notice all of them will have columns that. On a more holistic view, notice that if there was motion right here, something's forcing all of it down through here, like there's a vent or something that's pushing it down and to the right. I'm going to stop because I don't want to get too far into this and then have nobody know what I'm talking about. So I'm going to pause for questions real quick. Questions from you all? Yes. So you have to make a table each time. The table is the way I organize it. The AP test will not score you on making a table, but a table makes it really easy for the person who's grading it to see exactly what you did. And then again, going back you only have to get a 60-something% to get a 5. If they just look at your graph and they're like, oh, that's all wrong, then you get a 0 for it. But if they look at your table and they say, oh, this person's incapable of adding small, they know what they're doing in calculus, but they don't know what -3 + 1 is, then you get some points off that. That's why I advise you to make a table, as it's easy to follow your work. And again, remember, at the end of the day, I'm not grading this. So I want whoever grades yours to be able to give you that 4 or 5 that we've been talking about. And I'd hate for you to miss 5 points on this. Any others? Good question again from Batman. And just so you know, Brandon, I am doing the basketball game on Wednesday night if there is one. I could play the Batman theme when you walked out of there, like for number 20 for the Thunder, Brandon Storch, and then just play the Batman theme. Hearing no others, let's keep going. So again, I have to do this all for -2. And now that we've hopefully seen the pattern that whatever I plug in for x gives me the same value every time, I'm not going to do it for every single one again. Another question. So you just make the table with the slope for each x value, and then, yeah, but that's just for this one because there's no y in this one. As the next example, you'll see it depends on both x and y, so then we'll be able to see one that's a little more interesting than this one. This one's just nice one because it's only dependent on x. So I'm going to plug in -2 for x. We know that it doesn't even matter what the y value is, so I plug in -2 for x. -2 + 1 is -1. So again, I go to my chart. Now it's -1 for each one. -1, -1, -1, -1, -1. Okay, let's do it for -1. Extend the table. And 0, and 1, and 2, and 3. So if I plug in -1, -1 + 1 is 0. So, oops, sorry, that should go down here. 0. If I plug in 0, 0 + 1 is 1. 1 + 1 is 2. 2 + 1 is 3. 3 + 1 is 4. So if I go -1, my slope fields are at 0. So in other words, they're no slope. If I go to x = 0, it's 1. I go to 1, the slope dy dx is equal to 2, so a little bit steeper. If I go to 2, it's 3. So I'm going to actually draw one over here. Just imagine you got to go over 1 and up 1, 2, 3. So this is going to be pretty steep here. 2. And then if I go to 3, my dy dx, my slope is 4. So that's going to go 4, 4, 4, 4, 4. Now, Tara asked the question, how picky am I going to be grading on these slope lines? This is really where, well, first off, if it was this particular one, notice how it's getting steeper, steeper, steeper. That's what I'm looking for. Am I going to be counting tick marks? No, because really when we look at this, we're getting a general idea of what it's doing, and we can find a solution. Like if you put in like a drop of air here, what would it do? You could see where it would go. You can see where it would go through, but am I going to be looking to count over? No. First off, you don't have that kind of time on the AP test to be able to be that specific, but you can definitely tell like negative, more negative, 0, positive, more positive. Yep, and we'll look at, the next one we're going to do together is this one down here, and I think that one's a better one. You can look at some of these, and these are pretty simple, but am I going to be counting tick marks? No, and you don't have that kind of time on the AP test either. Okay, now particular solution will actually be like the line or the graph a particle would go through if you put it into this at a particular point. So imagine if we started at the point -2, 1. So we started right there. Okay, well, what's a particle going to do right there? We want to make the line look parallel to the lines around it. So notice that it's going like that. So notice it would go through there, it would go through there, it would go through there. But we'll talk about that in the next one. What I need you to do right now is we're going to look at number 6 on that sheet. And I just want you, I don't want to ruin your entire snow day here. Let's just look at this from -2 to 2 on X and Y. I will work the first couple for you, and then I'll ask you to finish it on your own. Again, I need to check to make sure my kids are still alive. I hear them, but I'm not sure that any limbs are still attached. Let's again draw a table for this. Our dy dx on this one is equal to -y over x. So now we notice it's dependent on both them, x and y. Yeah, do you have to do the point where x equals 0? Yeah, all the whole numbers between -2 and 2 on both x and y, including 0. So our equation on that is -y over x. We're going to look at x, we're going to look at y, and we're going to look at what that does to dy dx. X. And again, if you did this last year, which hopefully you did, because like I mentioned, a lot of points on the AP test. If you have a better way of organizing this, this is, again, just how I did it back in the day. So again, I'm going to start at I'm going to start at -2, 2, the upper left-hand corner there. And I'm just going to snake my way back and forth through. And again, I only have to do from -2 to -2 and from -2 to -2. So in other words, I don't have to do the 3 on both sides. And that's just so you don't have to spend the entire time doing that. So let's go through. So I'm going to start at -2 for x, 2 for y. My dy dx is -y over x. So -2 over -2 is going to give me a 1. So graphing that, I'm going to have a 1 there. Over 1, up 1, or again, that's y equals x through that point. So again, I just snake my way down. -2, -1, oh, -2, +1. So now I plug in 1 over -2. So it's going to be -1 over -2, which gives me 1/2. 1/2 is going to be getting closer to horizontal. I plug in 0, so -2, 0. Y is equal to 0. 0 over anything is going to give me 0. So notice it totally flattens out. And we can kind of notice positive, less positive, 0. It's probably going to go negative when we go down there. Okay, so -2, -1. Then I'll do -2, -2. -2, -1. So that makes it 1 over -2. So that's -1/2. And then -2 over 2. -2 over 2 is 1. Put the 1 in front. That's -1. So -1/2 and -1. Okay, there's my slope fields through this. So this one, kind of imagine it. I like to, picture things that are going on. So maybe there's, something magnetic or something air pushing it away from y equals, or x equals 0. No, y equals 0. Now, Thomas is asking about x equals 0. So I'm going to skip to that real quick. And like I said, I got to check on my kids. So I'm going to plug in -1. And then I got to do -1, 2. I got to do -1, 1. I got to do -1, 0. I got to do, I have to make some more tables down here. And you can see these are tedious. They are not simple. -1, 1, -1, 2. Okay, let's go to 0. So let's plug in 0, -2. Okay, so I've got 0 in my denominator, and we know that that leaves us as an undefined. Okay, is there a slope field with this? Yes. If 0 is straight horizontal, when we have 0 in the denominator, it's going to be straight vertical. So it's going to look like that at that point. And that can happen. I mean, that just means it's undefined. That happens. Stop and check up. Questions on that? Okay, I'm going to give you a minute, fill in the rest of them, and we'll go from there. Again, making a slope field is tedious, but nothing that's that mathematically hard. If anything, you just got to remember to be detail-oriented. Be right back. Good job, buddy. All right, I'm checking, but any questions on finishing that one up? Questions on that one? Okay, now notice with these, we do not have a full, like we don't have the equation, we just have a slope field. So we're graphing the derivatives, we're not graphing the original function. Good news is we are almost done with this lesson. I do have to tell you though, this is one where the last part, the last thing I'm going to talk about is probably the most challenging thing we're going to talk about all day, just because it's abstract. I'm even going to mooch some examples from the book to be able to help you with those. In fact, let me take a peek though. I'm going to skip to the next page of this. The next question we have to do is we have to match the slope fields with their differential equations. This is just some good practice on what's going on. Now, when we look at these, do we have to find every value? No, we just have to match them. So here's what I am going to look like on this. So here are my equations. Here's what I got. And here's the options I got for these. Okay, now remember that very first one we did that was just dependent on x. So we got one of these that's just dependent on x, one of these that's just dependent on y, one of these that has x and y, and one of them that has both just x. So here's the deal on this. The first thing I'm going to do is I'm going to look at this one that's just dependent on y, because that means for every y value, they should be the same. So in other words, when I look across like this, the y value should be the same, or the slope field should be the same for every y value. So as I look at this one, that doesn't work for that, doesn't work for that, doesn't work for that, but does work for this. Look as I go across, it's only dependent on y. So the values of y are, the slope fields are identical for the values of y. Also notice this one, if I plugged in 2 minus 2 is, that's where you say out loud 0. Okay, let's do that again. 2 minus 2 is, good job. And notice, what's the slope line doing at 2? It's equal to 0, so 9 matches with A. And again, I'm going to let you chime in with questions as you go through. The next two are just dependent on, two of them are dependent on x. So again, I'm kind of being smart here and going through. One of them is dependent on both x and y. So as I notice, this one, the differential fields or the slope values are the same for every x value, same for every x value. There's one that it's not, so that has to match up with D. Now, if that's not good enough for you, you're not feeling real secure about that, what you could do is you could plug in a point. Like let's pick on this point right here. This is at 1, 1. And notice the differential of the slope value is 0. Just to verify, 1 minus 1 is 0, so that one works out. And notice, if you plugged in 1 for that one, it doesn't equal 0. If you plugged in 1 for that one, it doesn't equal 0. And if you plugged in 1 for that one, it doesn't equal 0. So I know I talk fast, especially when there's nobody in front of me, but any questions on that before we go through the last two to see what happens? Okay, and then let's figure out which one's which. Okay, so I got dy dx is equal to x, and I got dy dx is equal to sine of x. Now let's review sine real quick. The sine of 0 is what? So I've got this one gone, I've got this one gone. The sine of 0 is what? Sine of 0 is 0, which you think would help us, but look, it's equal to 0 for both, because if you plugged in 0 over here too, you'd get 0. Shucks. What's the sine of 1? Okay, well, positive or negative? Okay, the sine of 1 is positive. It would mean 1 radian in this case, which isn't a huge number, but it'd be positive. The sine of 3 would be positive, 4 would be positive. What about the sine of negative 1? Well, then let's think back to our unit circle. If you went down 1 radian, would the sine of that be positive or negative? The sine would be negative. Okay, so we're noticing over here that it's negative. The sine of 2 would probably be negative 2. I don't know if that one feels good enough for me. Well, let's look at this one over here. If I plug in anything positive, I'm going to get a what? A positive. And if I plug in anything negative, I'm going to get a negative. So which one of these? If I plug in anything positive, it's going up. If I plug in anything negative, it's going down. Positive, up. Oh, yeah, but that one right there says that this one has to be B, and this one has to be C. Now, you may be saying to yourself, what? No, the sign of positive stuff. No, but remember, like, where is this right here? This is pi over 2. Remember, pi over 2. Pi is 3.14, so pi over 2 is going to be like 1.7, 1.6, 1.7. So if you have 2 radians, that's going to be more than that. If you have 3 radians, that's going to be over here. If you have 4 radians, it's going to be down here. So actually, a 4, 1, 2, 3, 4. It's going to be over here in the third quadrant. 4 radians is all the way over here. So then it should be a negative sign in that case. We have a question. Can't you just see the graph as C looks like the graph of y equals sine of x? It kind of looks like the graph of sine of x. But I like to be sure. Sometimes the defense comes out and it looks like they're going to blitz and they don't, and then I feel silly when I call a play that matches with blitz. So I'd like to know for 100% sure. And I know for 100% sure that one matches up with that. It looks like the sign, yeah, it does. Now, let's go to the last thing, a particular solution, and let's even pick on this sine graph right here. So let's say they asked you to find the particular solution of this going through the point, I don't know, let's go through the point 3, 2. When they say a particular solution to a slope fields problem, what they're asking you to do is draw in a graph that goes through 3, 2, that follows the trend of where the graph is going to go. What do you want it to do? You want it to look parallel to the points around it. Parallel to the points around it. So what would a line look like that's parallel here? It'd look like that. What's a line that's parallel here? It'd look like that. It'd look like that. Then here it needs to flatten out. What's it going to look like when it looks like that? It looks like that. It looks like that. It looks like that. It looks like that. This is challenging because you have to follow the slope fields of what's around it. So in other words, like I said at the start, you have to look and find the parallel ones around it. Oh, that's a negative. Yeah, duh, that's -3. Thank you, Batman. Thank you. That's a -3, obviously. It must be there or something. You're looking to trace and follow the slopes of the fields that are around it. Now, here's the good news on this. This is usually a 1. This is usually one that there's plenty of partial credit, like if you mix up, like especially like right in here. Like let's say you went down and then up and over. Okay, yeah, that's a 3-point problem. You got 2 out of the 3. But you're tracing around what it looks like around it. So let us take a look at an example that has that. Let us go down beneath here and let us trace neither one of those would have one. Let's go through. Let's go back to this original one. Let's go back to that. Nope, I don't want to clutter up your examples here. Let's take the one in the book that I was planning on using. Give me just a second to grab that out. If you got questions, this would be a perfect time for it. Okay, so let us look at this one real quick. So our directions are we have to, so we have our slope field here, and we're going to start at the point 1, 1 on this one. Let me get out my pencil here. I'm going to start at the point 1, 1. So over, and notice this is going up by 2. So that's not 1, that's 0.5, that's 1. So go up 1 is right there. Okay, so what's it going to be doing right there? It's going to be parallel to the lines around it. What's parallel to that? Parallel to the lines around it. What's going to be parallel in here? It's going to be parallel, so it's going to be looking like that. Probably even I need to make that parallel. Because notice I'm making it parallel to the ones around it, so it's actually probably going to go through that point. Okay, to make it parallel, I need to be going down. Okay, so I got to kind of compromise between these two. So I'm going to be looking like that. Parallel will put me in between here. Parallel, parallel, parallel. And notice how I'm kind of sketching and then I'm connecting my lines after I sketch. There would be my particular solution to that differential equation. So again, I'm making it look parallel to the ones around it that goes through that point. So notice to be parallel, I'm going to be going up and in between. I'm going to be going down, down, start to head up, go up, go up, go up. That would be my particular solution to that differential equation right there. Yes to whoever just asked. Yes, I'm writing my book. Okay, some questions that just came in. Is the line you draw in the graph of the derivative or the original function? It is the derivative. It is the solution set to the derivative. What will it tell us? It will tell us a function that will satisfy this differential equation. But I prefer to think of it as where are things going as they go through that slope field. So in other words, what will the solution tell us? It will tell us where things are going, but it is a derivative. It is a particular solution through that. Let me restate that because I think I just talked myself out of what I first said. Tara asked the question, is it going to be a function or a derivative? And remember, a particular solution is going to be a function whose derivative solves this equation. So when we find a particular solution, it will give us an original function. In other words, like if you had y is equal to c times e to the x, it will tell us what value of c we'd need to get that curve of the original function. Now, do you have to worry about that point right now? No, you don't. Why? Because we'll be able to solve that later on. That's when we separate variables, when we do various techniques to solve differential equations. All you have to find is a particular solution for it. What's a particular solution mean? Where's the graph going if I give you an initial condition of where it starts? Let's take a look at one more. Okay, let's look through this one right here. This is an example in your book, and don't look down below because there's some options for it to solve. Let's say that we start with 1 and it goes through -1, let's go -1, +1. Here's what I'd like you to do real quick. Just point at your screen real quick and find the solution, the particular solution to the differential equation whose slope field is modeled by that. Just trace it with your own. This one's pretty easy, so this one's pretty nice. Okay, so notice parallel through there would be that, parallel would be through that, parallel would be through that. What about this? Hi, Emily, how are you? Hello, Emily, how are you? Do you want to say hi to my class? Hi. You gotta say it loud so they hear you. Yes. Yes. Do you want to take calculus when you grow up? Yeah. Are you very excited to? Yeah. Are you very excited to learn about slope fields? Yeah. I'm almost a kid in it. You're almost a kid? Yeah, I'm almost getting this. Oh, you're almost getting it. I got you. I bet my students feel the same way. They're almost getting it too. Okay, can you let me finish real quick, honey? Benjamin is going there today. Benjamin is? Yeah. Okay, can you let me finish my class real quick? I'm almost done. Okay, so notice I started there. And again, I'm looking to go parallel to the ones around it, parallel to the ones around it, parallel to the ones around it, parallel to the ones around it. My calc teacher said you want to find the general pattern of what's going on. I always found that confusing because, like, generally I didn't know. This one's pretty easy, but if you look at even the one next to it, like, generally what's going on depends on how you weight the things around it. So there's the general solution to that one. I'll give you one more here. Let's say we start this one at 0, 1. So we start it right there. At this point right here, notice I'm trying to mimic the ones around it. Mimic the ones around it. In fact, that should probably go even steeper. And notice how I find myself just kind of like lightly shading in and then correcting as I see what's going around it. This one's tough because, okay, then what happens right here? I mimic the ones around it. So that's going to be going up and into that. Where's that going to be coming from? That's going to have to be coming from over here to be getting into it. What's it doing in there? It's flattening out and then going through there. And curve sketching is just that. It's sketching. It's finding the generalized pattern of what's going on around it. But again, my guidelines is I'm trying to go parallel to what's around it and follow the general contour of the curve. So you can imagine if a point started right here, this is where it would go through. Like, if imagine these were like the wind currents, this is where it would go through. Now, is it the same through everyone? No. Imagine I started right here. I'd be going down and down and down and up and up. So if I started through that initial condition, the curve looks very different. But we had some questions. Let's take those. For ones where it is not all the x's, are they the same? How do you know which slope field around it? And I'll be honest with you, that's just experience and talking through them. That's totally a question I expect to have come up after you guys do the homework on this, is like following the generalized trend of this. Again, I'm just kind of looking at the general pattern of what goes around it. Notice that one's going down even sharper. So we're definitely going down there. Again, down. Again, down, down, down. Yuck. But again, I'm looking at the 4 or 5 around it and trying to mimic the general pattern. Imagine like a particle going through a wind tunnel with this as its vectors. In fact, just to try to reiterate the point one more time, let's go next door. Let's do one more. Let's say a particle starts right here. What's it going to do? I've got this going up, this going up, this going flat, this going up. So I'm probably going to be going up. And then notice around here, it's definitely going up sharper, going up really sharp. What's happening is it goes over this way. And it's going up, flat, so I'm going over there. There would be my particular solution going through that point. Now here's the good news. Every point you start at is going to have a different particular solution. Some of them may look similar to each other, but not all of them are going to be exactly the same. But like I was mentioning at the start, that's the hard part of this, which is what we'd want to go through. Some other things to remember for what you have to do in your homework. Remember the tangent line. Like if we found, let me go back to my table real quick. And by the way, I'm not going to rat the person out, but whoever just said my daughter's really cute, oh, bonus points for you if extra credit wasn't against my religion. Okay, so if we're asked to find the tangent line at like this point right here, and let's call it -2, 1. Okay, question, how do we find the rate of change at that point? That's your dy dx. Remember, this is the slope of the tangent line at that point. Just don't forget, all the stuff you learn in calculus doesn't go away. dy dx at a point is the slope of the tangent line at that point. I'll wait for just a second. Questions on this? So it is kind of weird, but for your homework tonight, I'm actually just going to ask you to do out of that packet instead of the book per se. Because I just like these problems, and there's lots of AP problems in here, and you know what a big fan I am of AP problems. So here's what I'd like you to do on this. I'm going to ask you to do it from her section. I'm going to ask you to do 3 and 4 on here. I'm going to ask you to do the second part of matching the slope, which will be 11 through 14. I'm going to ask you to do 15 and 16. Those are, again, multiple choice. And again, notice how they're directly taken from the AP test. That's our target in this class. We want you to get a 4 or 5. That means we want you to do well in this test. Then the only part I'm going to ask a little flexibility on. 17, you need to do part A and part B. That's all we can do so far. And then 18, I'm going to ask you to do part A and part B. That's all we can do so far. I'm going to wait about a minute. Any questions before we go on or before I cancel the podcast for today? Thank you first off for doing this. I want to make sure that we cover everything to make sure you get that 4 or 5 on that AP test. I know I'm kind of drilling it through your head, but you guys are great kids. I will make sure you get scores that reflect how great you are as a kid. And like I mentioned, we don't want to have to make excuses for why we don't have good scores in calc. We just want to have good scores so we don't have to make excuses. So just because I love you and I want you to be happy, if there is a snow day tomorrow, I will have another one of these lessons that I post. It won't be as long as this one was, but I do want to make sure we're continuing to stay on that pace. Like I mentioned, I met with a lady from LP that's gets those amazing scores, and we're doing just fine for progress. There's no need to panic, but we just can't fall behind our current pace. So if we got snow days, we got to make these puppies up. And let me write down the whole assignment. Brandon, I got your message there. Here's the total assignment. 3, 4, 11 through 14, 15, 16, 17, part A and B, 18, part A and B. Let me know what you thought of this format too. You can just reply to the text. Let me know if this worked for you or not. I know it's not obviously ideal, but like I said, for snow day, yeah, it worked. I think this works pretty well to keep us on pace, but let me know your thoughts. The class is for you after all, and pause for about 5 more seconds, see if anybody else has got any questions. At one point, I had 10 viewers, so that's 2/3 of the class. Nobody else? All right, have a great rest of your day and enjoy your snow day, and hopefully Hatchell gives us another one tomorrow so we can do some more calculus. Otherwise, if it is a black day, we'll just take homework questions. Black days are a waste today. Sadly for you guys, though, I do not have your test graded yet because one of you slackers hasn't taken it yet. If you are that person, make sure that you take it soon. Tuesday would be a great day to get it just so we can then hand it back on Wednesday. But I don't have the ton of time to write another full version of this test for somebody else. So, yeah, have a great day, everyone. And again, thanks for watching.